Hi there, this is Miss Often, and this video is the first in a series that's going to talk about special segments and points in triangles. This video will cover all of the vocabulary related to special segments and points in triangles, and will provide a graphic organizer to help you organize the information about these special segments and points. By the end of this video, you'll be able to know and use vocabulary associated with special segments and points in triangles. You'll be able to prove and apply properties of perpendicular bisectors of a triangle, of angle bisectors of a triangle, apply properties of medians, and of altitudes of a triangle. So let's get started. Our vocabulary that you're going to need to know is concurrent, point of concurrency, perpendicular bisector and angle bisector you should already know, median, altitude may be familiar to you from previous geometry courses, circumcenter, incenter, centroid, and orthocenter are all going to come up in this video. Our first special segment is the perpendicular bisector. The perpendicular bisector of the side of a triangle bisects the side and is perpendicular to it. As such, it does not always pass through the opposite vertex. The three perpendicular bisectors of a triangle are concurrent, and this point of concurrency is the circumcenter of the triangle. This is because the point of concurrency, the circumcenter, is equidistant from all three vertices. Please note that this is equidistant. We're not talking congruence here, we're talking about distance. So the statement that goes with this diagram is that PA is equal to PB, which is equal to PC. If you want to talk about congruence, use the definition of congruence to say that PA is congruent to PB, which is congruent to PC. The circumcenter is also notable for being the center of the circle that contains all three vertices of a triangle. Now, the circumcenter can be inside the triangle, outside the triangle, or on the triangle. Here's an acute triangle. The circumcenter is located inside the triangle. In the obtuse triangle, the circumcenter is located outside the triangle. And in a right triangle, the circumcenter is located on the hypotenuse. Again, the circumcenter of ABC is the center of its circumscribed circle. And any circle that contains all of the vertices of a polygon is said to be circumscribed about the polygon. That just means drawn around. Next up are the angle bisectors. A triangle has three angles, so it has three angle bisectors. The angle bisectors of a triangle are also concurrent, and this point of concurrency is called the incenter of the triangle. Now, it's good to know that the incenter of a triangle is always located inside, just like its name, incenter. The incenter of a triangle is equidistant from the sides of the triangle. So looking at this diagram, PX is equal to PY is equal to PZ. Now you may be saying, what's up with those right angles? Well, we're not talking about perpendicular bisectors, but we do need to recall that the shortest distance from a point to a line, and the distance from a point to a line, therefore, is defined as the perpendicular distance from the point to that line or line segment. You'll notice that it is different distances from the vertices of the triangle in this acute triangle. Again, unlike the circumcenter, the incenter is always inside the triangle. There's some pictures, and it is the center of the triangle's inscribed circle. So a circle inscribed on a polygon intersects each line that contains a side of the polygon at exactly one point. Another way of saying this is that the circle is tangent to all sides of the polygon. Our third special segment is the medians of the triangle. Medians are special segments that connect the vertex of a triangle with the midpoint of the opposite side. The medians are concurrent at a point called the centroid of the triangle. Like the incenter, the centroid is always located inside the triangle. It's also called the center of gravity. It is the point where a triangular region will balance. We see here in triangle ABC that the midpoints are X, midpoint of side AB, Y, the midpoint of side BC, and Z, the midpoint of side AC. These segments AY, BZ, and CX are concurrent at point P, the centroid. The centroid of the triangle is located 2/3 of the distance from each vertex to the midpoint of the opposite side. That means that AP is 2/3 of the length of segment AY. PY, therefore, is 1/3 of that length. Similarly, BP is 2/3 of the length of the segment BZ, and CP is 2/3 the length of CX. Finally, the altitudes of the triangle are our last special segment. An altitude is a perpendicular segment from a vertex to a line containing the opposite side. Every triangle has 3 altitudes. Now I want you to notice here that an altitude can be inside, outside, or on the triangle. In this obtuse triangle, the altitude from side RS to vertex Q is inside the triangle. However, the altitude from QS to vertex R is outside the triangle. And we see this segment here goes from R to QS, and it's making a right angle there, actually goes outside of the triangle. Similarly, for the altitude going from the side containing, or the line containing side RQ up to vertex S, that is also outside of the triangle. So that means that special point of concurrency is going to be located in different places. This point of concurrency is called the orthocenter of the triangle, and it can be located inside on the vertex or outside. This summary table is very helpful. You may wish to pause the video for a moment and copy this into your notes. If you wish, you can also draw pictures of the perpendicular bisector, angle bisector, median, and altitude. Remembering, of course, that the altitude can be located entirely outside of the triangle, as we saw in our prior diagrams. In our next video, we'll look at some problems involving these special segments and the points of concurrency. See you there.